Errors, not exceptions. Idiomatic error handling in Go. 1. Introduction. The unavoidable truth of errors. Imagine a perfect world, a realm where software runs flawlessly, networks never falter, databases always respond, and user input is invariably pristine. In this idyllic digital landscape, every function returns precisely what you expect, every interaction is seamless, and every system operates with unwavering reliability. It's a comforting thought, a programmer's utopia. But alas, reality, as always, has a knack for intruding. The truth is, software, no matter how meticulously crafted, is an inherently imperfect creation operating within an imperfect world. Networks drop packets, hard drives fail, external services go offline, users type the unexpected, and even the most robust algorithms can encounter conditions beyond their intended scope. This is the unavoidable truth. Errors happen. They aren't just an annoyance, they are an intrinsic and inevitable part of building any robust software system. For decades, programmers have grappled with this fundamental challenge. How do we, as builders of these complex digital constructs, acknowledge, anticipate, and respond gracefully when things inevitably go awry? The way a programming language or an application handles these moments of imperfection often delineates the line between a brittle, unusable piece of software and a robust, reliable system that can withstand the unpredictable storms of the real world. Consider the user experience. Have you ever been using an application, perhaps filling out a crucial form, only for it to suddenly crash with an obscure message or, worse, just freeze? Or clicked a link on a website only to be greeted by a generic, "something went wrong" message without any indication of what happened or how to proceed? These are direct consequences of inadequate or poorly thought-out error handling. A user's trust in your software, and by extension your organization, is built not just on its ability to perform its core functions, but equally on its ability to gracefully navigate failure. From a developer's perspective, the impact is even more profound. Errors, if not properly managed, can cascade, turning minor glitches into catastrophic system failures. They can obscure the root cause of problems, transforming debugging into a frustrating, time-consuming quest for a needle in a haystack. An error that is caught, understood, and communicated effectively is a valuable piece of diagnostic information. An error that is ignored, swallowed, or mishandled becomes a ticking time bomb. Historically, programming languages and paradigms have approached this challenge with varied philosophies. Some have embraced mechanisms designed to interrupt the normal flow of execution when something exceptional occurs, providing a dedicated pathway for handling these deviations. Others have favored a more explicit approach, requiring developers to constantly acknowledge the possibility of failure at every step. Each approach has its proponents and detractors, its strengths and its weaknesses. In this book, we will embark on a journey to understand how modern software contends with the ever-present specter of failure. We will explore the differing philosophies that have shaped error handling across the programming landscape, delving into the concept of exceptions that dominate many popular languages. And then, our focus will sharpen on a language that has challenged the prevailing norms, offering a distinct and often counterintuitive approach. Go. Go, the programming language that emerged from Google, was designed with simplicity, concurrency, and reliability at its core. And central to its design philosophy is a unique perspective on failure. Errors are not exceptional events to be handled out of band. They are values, just like numbers or strings, that flow through your program and must be explicitly dealt with. This seemingly simple design choice has profound implications for how Go programs are structured, how robust they become, and how developers think about the inevitability of things going wrong. For those familiar with other languages, Go's approach can initially feel unconventional, perhaps even verbose. But beneath this surface lies a powerful philosophy that fosters clarity, encourages rigorous thinking about failure scenarios, and ultimately leads to more reliable, maintainable software. Throughout this book, we will demystify Go's approach to error handling. We'll explore the rationale behind its design, contrast it with the exception-based paradigms, and provide clear, practical guidance on how to write robust, idiomatic Go code that embraces the unavoidable truth of errors. transforming potential pitfalls into opportunities for resilient and reliable software. Welcome to the world where errors are not just caught, but valued. 2. The exception paradigm, a different path. To truly appreciate Go's distinct approach to error handling, it's crucial to understand the alternative and arguably dominant paradigm in modern programming. Exceptions. Exceptions are a mechanism designed to handle abnormal or exceptional conditions that disrupt the normal flow of a program. They represent a fundamental shift from earlier forms of error management, such as returning special error codes or setting global error flags. Let's journey back a bit. In the early days of programming, languages like C often relied on return codes. A function would return an integer, with 0 often signifying success and any non-zero value indicating a specific error. Imagine a simple file reading function. Int read file, const char file name, char buffer, int maxlen. After calling read file, you'd have to check its return value. If it was -1, perhaps it meant file not found. -2, permission denied, and so on. This approach made error checking explicit, but it could also lead to verbose code, where every function call was followed by an if statement, cluttering the primary logic. Crucially, it was easy to forget to check the return code, leading to silent failures or undefined behavior. As programs grew more complex and object-oriented programming began to take hold, the need for a more structured and robust error handling mechanism became apparent. This fertile ground gave rise to the concept of exceptions. Exceptions, interrupting the flow. The core idea behind exceptions is that when an exceptional event occurs, something that prevents a function from completing its intended task, the function doesn't just return an error code. Instead, it throws or raises an exception. This exception then propagates up the call stack, effectively unwinding the execution path until it's caught by a try-catch or try-except in Python block designed to handle that specific type of exception. Let's consider a common scenario in many object-oriented languages like Java, C++, Python, or C#, trying to connect to a database. In a traditional return code system, you might have result equals connect to database, MyDB, if result equals success. Handle error. With exceptions, the code might look like this conceptually. Try. Connection equals connect to database, MyDB. Use the connection. Catch, database connection exception E. Handle connection error. Log message, failed to connect to database, plus eGet message, display error to user, cannot access data at this time. Please try again later. Catch permission denied exception E. Handle permission error. Log message, permission denied to database, plus eGet message, display error to user, you do not have permission to access this. Contact support, finally. This block always executes, regardless of whether an exception was thrown or caught. Useful for closing resources, like the database connection. If connection null, connection close. Here's a breakdown of the key elements. Try block. This encloses the code that might throw an exception. It represents the normal execution path. Catch blocks. These blocks are executed only if an exception is thrown within the try block and the exception's type matches the type specified in the catch clause. This allows for different types of errors to be handled distinctly. Throw raise. This statement is used by the code encountering the exceptional condition to signal that something went wrong. Finally block or ensure in Ruby. This optional block is guaranteed to execute whether an exception was thrown or not, and whether it was caught or not. It's invaluable for cleanup operations, like closing files, network connections, or database handles, ensuring resources are released even in the face of errors. Advantages of the exception paradigm. Separation of concerns. Exceptions allow you to separate the normal execution logic from the error handling logic. Your primary code path remains cleaner, untainted by frequent if equals nil checks. Explicit error propagation. When an exception is thrown, it unwinds the call stack automatically. You don't have to explicitly pass error codes up through multiple layers of functions. If a function doesn't know how to handle an error, it simply doesn't catch it, and it continues to propagate upwards until a suitable handler is found or the program terminates. Type safety in some languages. In languages like Java, Exceptions are often part of the type signature of a method, checked exceptions. This means if a method can throw a certain type of exception, callers are forced by the compiler to either catch it or declare that they also throw it. This theoretically makes error handling more explicit and prevents silent failures. Rich error information. Exception objects can carry a wealth of information, including messages, stack traces, and even nested cause exceptions, making it easier to diagnose the root problem. Disadvantages and criticisms. While exceptions offer significant benefits, they are not without their criticisms and challenges. Complexity and obscurity of control flow. The flow of control, especially in languages with many nested try-catch blocks or deep call stacks, can become difficult to predict. It's not always obvious where an exception will be caught or what code might execute as part of a finally block during unwinding. This can make debugging challenging. Performance overhead. Throwing an exception, particularly in performance-sensitive code, can incur a significant overhead due to the creation of stack traces and the unwinding of the call stack. For this reason, exceptions are generally reserved for truly exceptional conditions, not for common expected failures like a file not existing. Checked versus unchecked exceptions. This is a long-standing debate. Java's checked exceptions force developers to handle or declare every possible error, leading to verbose throws clauses or empty catch blocks that swallow errors. Unchecked exceptions, runtime exceptions, on the other hand, allow errors to propagate freely, which can lead to uncaught exceptions crashing the program if not handled at a high enough level. Finding the right balance is tricky. Abuse of exceptions. Due to the convenience of automatic propagation, developers sometimes use exceptions for normal control flow, treating them almost like go-to statements for jumping out of loops or functions. This, however, violates the principle that exceptions should be for exceptional conditions, leading to code that is hard to read and debug. Side effects during unwinding. If a finally block or a catch block performs an action that itself throws another exception, it can lead to complex and hard-to-reason-about behavior. The problem of exceptional definitions. One of the subtler yet profound criticisms lies in the very definition of exceptional. What truly constitutes an exceptional condition? Is a user entering invalid data exceptional? What about a file not being found, or a network timeout? Many errors, while preventing normal operation, aren't necessarily rare or catastrophic. They are expected failures that need to be handled. When everything that can go wrong is treated as an exception, the keyword loses its meaning, and the advantages of separation can turn into a tangled web of error handling. This conceptual ambiguity, combined with the practical challenges of control flow and performance, led some language designers to seek a different path. A path where the unavoidable truth of errors is addressed not by interrupting the flow, but by integrating error handling directly into the program's normal data flow. And that path leads us directly to Go. 3Go's philosophy, errors as values. Having explored the landscape of exception-based error handling, we now turn our attention to Go, a language that deliberately chose a different path. Go's creators, notably Rob Pike, Robert Griesemer, and Ken Thompson, eschewed exceptions not out of ignorance, but from a deeply considered philosophy rooted in simplicity, explicitness, and clarity. Their core tenet: errors are values. This isn't just a linguistic quirk, it's a fundamental design decision that permeates the entire Go ecosystem. In Go, an error is essentially a specific type of value, typically represented by a special error interface. When a function might encounter a problem, it simply returns an error value alongside its regular return values. There's no sudden jump in the call stack, no special try-catch blocks, no hidden control flow. The flow of execution remains linear and predictable. The error interface, simple yet powerful. At its heart, Go's error handling mechanism is built around a single, humble interface. Type error interface. Error, string. That's it. Any type that implements an error. Method, which returns a string, is an error. This simplicity is a hallmark of Go, allowing for incredible flexibility while maintaining a minimal surface area for understanding. The most common way to create an error value is using the built-in errors package, specifically errors, new, import errors. Inside a function, if something is wrong, Return errors new, something went wrong. Or more commonly end with more formatting capability, FMT error. Import FMT. Inside a function, if do something, equals nil. Return FMT error, failed to do something, %w, more on %w later. Both errors, new and FMT error, return values that satisfy the error interface. Multiple return values, the enabler, Go's unique capability to return multiple values from a function, is the practical foundation upon which its error handling philosophy stands. Most Go functions that can fail will return two values, the result of the operation and an error value. If the operation succeeds, the error value will be nil. If it fails, the error value will be non-nil, and the result value will typically be its zero value or an otherwise undefined value, which should be ignored. Consider a function that attempts to read data from a file. Func read config, filename string, byte error. Data equals osread file, filename osread file returns byte error. If equals nil, here is a non-nil error value, indicating failure. We handle it or propagate it. Return nil FMT error, could not read config file %s, %w, filename Here is nil, meaning the read was successful. Return data, nil. This pattern value, equals function call, followed immediately by if equals nil, is omnipresent in Go code. It is so common and so fundamental that it defines the rhythm and structure of Go programming. Explicitness over implicit mechanisms. Go's choice to treat errors as values reflects a deep preference for explicitness. When a function returns an error, the caller must acknowledge it. The compiler won't let you simply ignore a non-nil return value. While you can use the blank identifier to discard an error, doing so is a conscious decision and usually reserved for specific, rare scenarios where the error is truly irrelevant or cannot be handled. For example, discarding error intentionally if it's truly not important. Equals FMT println, hello Go. But even then, often you'd still want to log it if it indicates a problem. If equals nil, logprint failed to print, %v, This immediately addresses one of the major criticisms of return code-based systems, the ease of forgetting to check an error. In Go, forgetting to use the error value effectively creates an unhandled variable, which the compiler often flags or leads to a logical gap that becomes immediately apparent. The rationale behind the choice. Why did Go's designers opt for this approach? Clarity and predictability of control flow. With errors as values, there are no hidden jumps or unexpected unwinding of the stack. The control flow is always explicit and local. You look at a function call, and you immediately see what values it returns, including the error. This makes reasoning about code much easier, especially in complex concurrent systems. Encouraging error handling. The if equals nil pattern forces developers to think about error conditions at the point of call. It encourages them to consider potential failures as part of the normal operation of a function, rather than as exceptional events that might be handled globally or much later. This fail fast, fail explicitly mindset leads to more robust software. Simplicity, the error interface is minimal. There's no complex hierarchy of exception types to learn, no intricate rules about checked versus unchecked exceptions. The mechanism itself is straightforward, allowing developers to focus on what constitutes an error and how to handle it, rather than how to use the error handling mechanism. Performance. Throwing and catching exceptions in languages with robust runtime environments can involve significant overhead, including stack unwinding, creating stack traces, and searching for handlers. Go's approach, returning a simple value, has negligible performance impact. This allows errors to be used for a wider range of failure conditions, even somewhat common ones, without performance penalty. Composition. Because errors are just values, they can be passed around, stored, combined, and compared just like any other data type. This enables powerful patterns for error aggregation and introspection, which we will explore in later chapters. Avoiding abusing exceptions for control flow. By not providing an exception mechanism, Go naturally steers developers away from using exceptions for normal control flow, which is often considered an anti-pattern in other languages. Is panic Go's exception? Go does have a mechanism called panic and recover. Superficially, they might resemble exceptions. A panic immediately stops the normal execution of the current function and begins unwinding the stack, running any defer functions along the way until a recover call is encountered or the program terminates. However, Go's official documentation and community consensus are very clear. Panic is not for general error handling. It is reserved for truly unrecoverable conditions, typically indicating a programmer error, e.g., dereferencing a nil pointer, out-of-bounds array access, or a catastrophic failure where the program cannot continue safely. It's akin to a fatal error condition that should ideally halt the program, allowing an operator to intervene. Using panic for expected error conditions is considered an anti-pattern and often leads to brittle and hard-to-debug code. We will delve deeper into panic and recover in a dedicated chapter. Embracing the Go way. For developers coming from exception-heavy languages, Go's error handling can feel alien or even cumbersome at first. The constant if equals nil checks might seem verbose, especially for functions that return many errors. But this initial discomfort often gives way to an appreciation for the clarity, explicitness, and robustness it fosters. In Go, errors are not an afterthought. They are a first-class citizen of your program's logic. By treating them as values, Go forces you to acknowledge the imperfections of computation and build resilience directly into the fabric of your applications. This paradigm shift encourages a more disciplined and thorough approach to building reliable software, equipping you to handle the unavoidable truth of errors with grace and precision. 4. Handling errors. The idiomatic Go way. Now that we've grasped Go's fundamental philosophy, that errors are merely values, it's time to dive into the practical application. How do Go programmers actually handle these error values in their day-to-day coding? The answer lies in a pattern so ubiquitous that it's almost synonymous with Go itself: the if equals nil check. The ubiquitous if equals nil pattern. In Go, when a function returns a potential error, the very next thing you typically do is check if that error is nil. If it's not nil, it means something went wrong, and you must then decide how to react. Imagine a simple scenario. You're trying to open a file. In Go, an operation like open attempts to return a file handle and an error. Your code would look something like this. First, a function call that might produce an error. File equals open mydocument.txt. Here, file would be a variable representing the opened file, and would be a variable of type error. Immediately after this line, you perform the check. If equals nil. An error occurred. Now decide what to do. This sequence is not boilerplate. It's a deliberate and highly explicit handshake between the function that might fail and the code that uses its result. It forces you, the developer, to always consider the failure case right alongside the success case. 2 primary responses to an error. Once you detect that is not nil, you generally have 2 main choices: handle the error locally and possibly recover. This means that your function knows how to deal with this specific error. Perhaps it can retry the operation, log the issue, and continue with a default value, or inform the user in a way that allows them to correct the problem. Return the error, propagate it upwards. More often than not, a function doesn't have enough context or capability to fully fix an error. In such cases, the idiomatic Go way is to simply return the error value to its caller, possibly adding more context along the way. This allows the error to bubble up the call stack until it reaches a point where it can be handled meaningfully, or eventually, where the program decides to exit. Let's illustrate with our file opening example. Scenario A. Handling locally, if appropriate. Suppose your application configuration lives in a file, but if that file isn't found, you want to use a set of default settings instead. Attempt to open the config file. Config data, read config file, appconfig.json. Check for error. If equals nil. If the error indicates file not found, use defaults. More advanced error checking with errors will be covered later. If OS does not exist, log print config file not found using default settings. Config data equals get default config. Else, for any other file-related error, it's more serious. Log fatal error reading config file, %v. Now, continue processing with config data. In this case, the read config file likely returned an error, but because we could recover from a specific type of error, file not found, we chose to handle it. For other errors, we decided it was a fatal condition, leading to the program's termination, log fatalf. Scenario B, propagating the error, the most common case. Far more frequently, your function will encounter an error it can't meaningfully resolve. It receives an error from a function it calls, and its job is merely to pass that error along to its caller, perhaps with some added context. Consider a function designed to save user data to a database. If the database insertion fails, this save_user function probably can't fix the database. Its responsibility is to report the failure. Func save_user, user error. Call a lower-level function that interacts with the database. equals database.insert user. Check for an error from the database operation. If equals nil, we can't fix the database insertion here, so we return the error, possibly enhancing its message. Return fmt errorf, failed to save user %s to database, %w, user ID If we reach here, no error occurred, so return nil. Return nil. Notice the pattern, return fmt errorf. Additional context, %w, originaler. This not only returns the error but crucial adds context to it. This technique, called error wrapping, is incredibly powerful for debugging and will be detailed in the next chapter. For now, understand that you're creating a new error that contains the original one, giving the next caller more information. When save_user is called, its caller will perform its own if equals nil check and decide its next course of action. This explicit chain of error propagation makes the flow of error information very transparent, a stark contrast to the implicit unwinding of exceptions, creating basic errors. As mentioned in the previous chapter, Go provides simple ways to create errors. Errors new, some message. Use this for simple, constant error messages where no variable data is needed. For instance, a function might return errors new, invalid input. fmt errorf, formatted message. %v, variable. This is the more common and vastly more flexible way to create errors, allowing you to include dynamic data and context within the error message. The format string works just like fmt_sprintf. We use %v for general values and, crucially, %w for error wrapping, which we reiterate will be a key topic soon. For example, creating an error with dynamic information. If amount lesser equals 0, return fmt errorf, cannot process transaction with non-positive amount, %.2f amount. The imperative of not ignoring errors. Perhaps one of the greatest strengths of Go's error handling, which stems directly from the explicit if equals nil pattern, is the strong discouragement of silent error omission. In languages where exceptions are thrown, it's all too easy to simply not implement a try-catch block, allowing an exception to propagate and eventually crash the program or be caught by a very high-level generic handler that logs a cryptic message. Go's design makes ignoring errors significantly harder to do accidentally. While you can use the blank identifier to explicitly discard an error return value, e.g., some func, where you then never use doing so is rare and almost always a bad idea for operations that can fail. An anecdote. Consider a real-world scenario where a startup, eager to get features out, had a critical payment processing system written in a language with exceptions. During a period of high load, an external payment gateway began returning intermittent network errors. The code path that called the gateway was inside a try block, but the development team had chosen to put only a generic catch block that simply logged an error occurred. The specific network error was never inspected, and no retry logic or fallback was implemented for that specific case. Customers' payments were failing silently, leading to lost revenue and customer frustration, all because a specific error type wasn't explicitly considered and handled. In Go, had that payment gateway call returned an error, the developer would have been immediately presented with the if equals nil check. This would have naturally led them to consider, what kind of error can I get here? What should I do if the network fails? Should I retry, or inform the user, or log a specific alert? The explicit nature of the check forces this critical thinking. Unhandled errors in Go lead to unpredictable behavior, corrupted data, or program crashes. The if equals nil pattern is your first line of defense, a constant reminder to acknowledge and address the inevitable imperfections of the digital world. It promotes a defensive programming style, encouraging you to always think, what if this goes wrong? And to build your applications with resilience from the ground up. This constant vigilance, while seemingly verbose at first, quickly becomes second nature and is a cornerstone of writing robust Go applications. 5. Beyond the basics, custom errors and contextual information. While errors, new and FMT error are incredibly useful for generating simple error messages, they often fall short when you need more than just a string to describe what went wrong. In real-world applications, an error is rarely just a file not found message. It might be file config.json not found in path app data, attempted by user admin on server web01 at 2023-10 to 26:10:35 UTC, original error. Permission denied. This kind of detailed information, often referred to as contextual information, is crucial for debugging, logging, and making intelligent decisions about how to handle specific error conditions. Go provides elegant mechanisms to achieve this: custom error types and error wrapping. Creating custom error types. Because Go's error interface is so minimal, type error interface error. String, you can make any struct or type into an error simply by implementing the error method. This allows you to define specific error types that carry richer, structured data beyond just a string message. Why use custom error types? Semantic meaning. Instead of comparing error messages, which is brittle, you can compare error types. This allows you to specifically handle different kinds of failures. Structured data. You can embed relevant information directly into the error object itself, rather than trying to parse it out of a concatenated string message. Readability. Code that checks for if errors is, error or file not found is often clearer than if error equals file not found. Let's define a custom error type for a file operation failure. Package main. Import. FMT. Us. Time. Define a custom error type as a struct. Type file error struct. Path string. Operation string. Timestamp time. Error the original underlying error. For wrapping. Implement the error method for file error. Func file error string. Return FMT sprint. File operation failed. %s on path %s at %s original error. %v. Fee operation, fee path, fee timestamp format, time RFC 3339, fee error. Now, instead of returning a generic FMT error, a function could return an instance of file error. Func load file path string byte error. Data equals os read file path. If equals nil, populate our custom error with rich context. Return nil and file error. Path. Operation, read. Timestamp, time now. This is the wrapping part. Return data, nil. This file error object now carries the path, operation, and timestamp information inherently. If you receive this error, you can check its type and then access these fields programmatically. Error wrapping, preserving the chain of causation. In the file error example above, you might have noticed the error field used to store the original osread file error. This is a crucial concept, error wrapping. When a function encounters an error from a dependency, e.g., a database driver, a network call, a file system operation, it often needs to add its own context to that error before returning it. However, simply creating a new error message that includes the original one as a string leads to a problem. You lose the ability to programmatically inspect the original error. Consider this. If osread file returns an ospath error, and your load file function just creates a FMT error, could not load file, %v, the caller of load file can only see the string. They can't ask, was this specifically an ospath error caused by a permissions issue? Go 1.13 introduced built-in support for error wrapping, which solves this problem elegantly. The key lies in the %w format verb with FMT error and two new functions in the errors package, errors, is, and errors, as. How to wrap an error %w. When you use the %w, wrap, verb with FMT error, it tells Go that the error value provided as the second argument is the wrapped error. The new error object effectively contains the original error, allowing for a chain of errors to be preserved. Import FMT. Import errors for errors is and errors as later. Type database error struct. Query string. Code int. Error, the underlying database driver error. Func to database error, string. Return FMT sprint. Database query %s failed with code %d. %s dequery to .code error. Func connect to db con str string error. Simulate a connection error. Return and database error. Query connect. Code 1001. Errors new network unreachable. This is the root cause. Func get user data user query string error. Connect to db some connection string. If equals nil, here we wrap the database error, adding more context. Return FMT error. Failed to retrieve user data for query %s. %w user query Return user data nil. Assume success otherwise. Now, if get user data returns an error, the error chain looks something like this. Failed to retrieve user data. Wrapped database query connect failed. Wrapped network unreachable. Inspecting wrapped errors is and errors as. With errors being wrapped, how do you inspect them? Simply using == will only work for unwrapped errors. You need the functions errors, is and errors as. Errors is target error. This function recursively unwraps an error chain and reports whether any error in the chain matches target. It's ideal for checking against specific sentinel errors, predefined error variables, or known error types. Let's define a sentinel error for a file not found scenario. Define a sentinel error for file not found. Var not found equals errors new, not found. A function that might return not found or wrap it. Func read data filename string byte error. Data equals os read filename. If equals nil, if os does not exist, error. If the underlying error is file does not exist, return our sentinel. Return nil not found. For other errors, wrap them with more context. Return nil FMT error. Read operation failed on %s. %w filename Return data nil. Func process file path string error. Equals read data file path. If equals nil, if errors is error not found. FMT print info. The file %s was not found. Using default \n file path. Return nil handled, no error. For any other error, propagate it. Return FMT error, processing file %s failed. %w file path Return nil. In process file, errors is error not found will correctly identify if not found is anywhere in the error chain, regardless of how many layers of wrapping are on top of it. This is a robust way to check for specific error conditions without relying on string comparison. Errors as target any. While errors is checks if an error in the chain is a specific error value, errors as checks if an error in the chain can be assigned to a specific error type. If a match is found, it populates the target, which must be a pointer to an error type with the concrete error value. This allows you to extract the custom error itself and access its structured fields. Let's use our database error example, func main. User data equals get user data, some user ID. This returns an error wrapped with database error. If equals nil, FMT println error prints the full wrapped error message. Var db error database error declare a variable of our custom error type. Important. It must be a pointer to the type. If errors as error and db error. If the error chain contains a database error, db error will now hold it. FMT print specific database error detected \n. FMT print query %s\n db error query. FMT print code %d\n db error.code. FMT print original db driver error %v\n db error. Else FMT println no specific database error found in chain. Else FMT println user data. In this main function, errors as error and db error attempts to find a %database error within the chain. If successful, db error will point to that database error instance, allowing you to access db error query db error.code. etc. This is incredibly powerful for analyzing specific error conditions at higher levels of your application without imposing a rigid error hierarchy. A word on type assertions. Before errors, as developers might have used type assertions like if customer, okay, equals error, my custom error, okay. While this still works for unwrapped asterisk errors, as is the correct and idiomatic way to handle error chains as it recursively unwraps. Use errors, as for checking types within wrapped errors. By combining custom error types with error wrapping, Go provides a flexible and powerful system for not only signaling that something went wrong, but also for conveying rich, structured, and inspectable information about the failure. This deepens your ability to diagnose problems, implement sophisticated recovery strategies, and ultimately build more reliable and debuggable applications. 6. When things go wrong. Panic and recover. We've firmly established Go's stance on errors as values, and how the if-er equals nil pattern is the idiomatic way to handle expected failures. However, Go does possess a mechanism that superficially resembles exceptions. Panic and its counterpart, recover. It is critically important to understand that panic is not Go's general-purpose error handling mechanism. Instead, it serves a very specific and much narrower purpose. What is a panic? A panic in Go indicates that something truly unexpected and unrecoverable has occurred. It signifies a program state that is so broken or inconsistent that the application cannot reasonably continue its normal execution. Think of it as the program screaming for help, reporting that it has hit a logical dead end or an unforeseen critical flaw. When a function calls panic, either explicitly panic, something terrible happened, or implicitly, e.g., a nil pointer dereference, an out-of-bounds array access, or a division by 0, the following happens. Immediate cessation. The normal execution of the current function stops instantly. Stack unwinding. The runtime begins unwinding the call stack. This means it jumps out of the current function, then the function that called it, and so on, moving up the chain of function calls. Deferred functions execute. Crucially, during this unwinding process, any defer statements encountered in each function on the stack will execute. This unique feature makes defer invaluable for cleanup operations, like closing files or database connections, that must happen regardless of whether the function returns normally or panics. Program termination, default. If the unwinding process reaches the top of the call stack, the main function or the start of a Go routine, without being intercepted, the program terminates, usually printing a full stack trace to standard error. Panic versus error, a crucial distinction. The key difference between an error and a panic lies in their semantics and severity. Errors, values, represent expected problems that a well-written program should anticipate and handle gracefully. Examples: file not found, network timeout, invalid user input, failed database query due to unique constraint violation. These are often recoverable or can be dealt with by the calling code. Panics represent unexpected and unrecoverable programming errors or catastrophic conditions. Examples: nil pointer dereference, your code tried to use a variable that was nil when it shouldn't have been, an assertion failure, a logical path that should theoretically be impossible to reach. These typically indicate a bug in the program itself, not just an external failure. Analogy: imagine your program is a car. An error is like a flat tire, an anticipated issue. You pull over, change the tire, and continue your journey. It's a bump in the road, but the trip continues. A panic is like the engine exploding, a catastrophic, unexpected failure. The car program stops completely. You're not changing a tire, the car is no longer functional. When to use panic idiomatic scenarios. Given this strict definition, panic should be used very sparingly, and only in situations where the program cannot continue in a sensible way. Unrecoverable initialization errors. If your program cannot properly initialize itself, e.g., it absolutely requires a database connection to start, but the connection string is invalid, panicking might be acceptable. This signals that the program cannot fulfill its purpose and should not try to proceed. Func init database. SQL open, Postgres, invalid connection string. If equals nil, this is a critical startup error. Program cannot proceed without DB. panic FMT sprint, failed to connect to database. %v, proceed with using con. Func main, init database, if panicked, main will cease. Rest of the program. Even in this scenario, some argues that returning an error from init database and letting main decide to log fatal, which internally calls osexit, is a cleaner approach than panic. The key is that the program's execution stops. Violations of fundamental invariants, developer bugs, if your code reaches a state that should logically be impossible due to programming errors. For instance, if a certain data structure is expected to always contain an element, and it's found empty, that might warrant a panic during development or testing to catch the bug. Fatal errors in tools scripts. For command line tools or one-off scripts where a failure means the tool simply can't do its job, panicking might be an acceptable quick exit. Recovering from a panic. While panics are generally intended to terminate the program, Go provides a built-in function, recover, which allows you to regain control after a panic. Recover is only useful inside a defer function. When recover is called within a deferred function and a panic is currently active, recover stops the unwinding process and returns the value that was passed to panic. If no panic is active, or if recover is called directly, not within a defer, it returns nil. Here's how recover is typically used. Func protect run ffunc. Defer func. If r equals recover. R equals nil. A panic occurred, we caught it. FMT print, recovered from panic. %v\n. R, you can log the stack trace here, if needed for debugging. A debug print stack. The deferred function must be called immediately. F, execute the function that might panic. Func might panic, int. If i5, panic, value too high. FMT print, might panic executed with %d\n. I. Func main, FMT println, starting program. Protect run func, might panic 3, might panic 7, this will panic. Might panic 1, this line will not be reached. FMT println, program continued after potential panic. This line is reached. In this example, when might panic 7 is called, it panics. The deferred function in protect run catches it with recover, prints a message, and allows the main function's execution to continue. Without protect run, the program would have terminated after might panic 7. Idiomatic use cases for recover. The primary, widely accepted use case for recover is to gate potentially unreliable code, especially in long-running services like web servers. Web servers / concurrent services. Imagine a web server handling user requests. Each request is typically processed in its own goroutine. If one goroutine panics due to a bug in handling a specific request, you don't want the entire server to crash and stop serving other valid requests. In such a scenario, a common pattern is to wrap the request handler for each goroutine with a recover block. Func handler, W HTTP response writer, R HTTP request. Defer func, if R equals recover. R equals nil. Log print, recovered from panic in HTTP handler. %v\n R. HTTP error, W, internal server error. HTTP status internal server error. Your actual request processing logic. Potentially call functions that could panic. For example, if you had a bug that caused a nil pointer dereference here, var data my struct, FMT println data field, this would panic. In main or an HTTP server setup, HTTP handle func / handler. HTTP listen and serve, 8080 nil. This pattern ensures that a panic in one request only affects that specific request, serving a generic error to the client, logging the incident, and allowing the server to continue handling other requests. Warnings and anti-patterns. Using panic and recover too liberally can lead to code that is hard to reason about. The non-local jump caused by panic makes control flow difficult to track compared to explicit error returns. Bug masking. Repeatedly recovering from panics can hide underlying bugs rather than forcing their resolution. Performance overhead. Panicking and recovering is significantly slower than simply returning an error value. Crucial rule. Never use panic for expected error conditions. If a function can reasonably fail due to external factors, network, file system, invalid user input, it must return an error value. Panic is for developer errors or truly catastrophic, unfixable states. In summary, Go's panic and recover mechanism is a potent tool, but it's a tool for specific, drastic situations. It's akin to an emergency shutdown button or a last resort safety net around critical services. It is not, and should not be treated as, a replacement for Go's core error as value philosophy, which remains the principled and preferred way to manage the inevitable imperfections of software. 7 strategies for robust error management in Go. Armed with an understanding of Go's error as value philosophy, custom error types, error wrapping, and the judicious use of panic recover, we can now synthesize these concepts into practical strategies for building truly robust applications. Effective error management in Go isn't just about catching errors. It's about minimizing their impact, providing clear diagnostics, and designing systems that gracefully handle unforeseen circumstances. 1. Don't ignore errors. This is the golden rule. We've touched upon it, but it bears repeating. Never ignore errors. Every function that returns an error requires explicit consideration. If you call an API that returns an error, but you don't check it, you are consciously choosing to let your program continue in an unknown state when something has indicated a problem. This is a primary source of subtle, hard-to-debug issues later on. Anti-pattern, ignoring the potential error. F equals oscreate, log_file_txt. F write string, starting application, \n, what if file creation failed? Write string would fail too. The correct approach, f equals oscreate, log_file_txt. If equals nil, log fatalf, failed to create log file, %v, fatal because we need logs. Defer fclose, ensure file is closed even on panics or early returns. Equals fwrite string, starting application, \n. If equals nil, log print, warning, failed to write to log file, %v, log but continue if logging isn't critical. Even if you genuinely believe an error cannot happen, logging it, even as a warning, can be invaluable during debugging or unexpected deployments. 2. Add context with error wrapping. As discussed in Chapter 5, simply propagating an error isn't enough. When an error bubbles up several layers, its original, unadorned message might lose meaning. Your function should add its own context when wrapping and returning an error. Bad. Obscures original error's context. Func load user, dstring, user error. Row equals db query row, select from users where ID equals. Id. User equals and user. Equals row scan, and user ID. And user.name. If equals nil. If equals SQL rows. Return nil, fmt errorf. User %s not found, id lost potential db error. Return nil, fmt errorf, failed to load user, completely generic. Return user, nil. Good hey. Preserves and augments context. Func load user, dstring, user error. Row equals db query row, select from users where ID equals. Id. User equals and user. Equals row scan and user ID, and user.name. If equals nil. If errors is SQL no rows. Return nil, fmt errorf. User with ID %s not found. %w. Id, user not found, custom error if we intend specific handling. Wrap the original database error, adding our context. Return nil, fmt errorf. Failed to scan user data for ID %s. %w, id, Return user, nil. The %w verb and errors is errors, as are your best friends here. They allow you to add high-level context, e.g., failed to process order, while preserving the low-level details, e.g., database connection refused. 3. Design explicit error types for specific handling. Don't just rely on string matching to identify error conditions. Define custom error types or sentinel errors when the caller needs to programmatically distinguish between different classes of errors. Define a sentinel error for user not found. var user not found equals errors new, user not found. Define a custom error type for complex validation issues. Type validation error struct. Field string. Message string. Func v validation error, string. Return fmt sprint. Validation error for field %s. %s, v field, v message. Example usage. Func create user, name, email string error. If name equals, return and validation error field, name, message, cannot be empty. If email equals, return and validation error field, email, message, cannot be empty. Actual creation logic, return nil. Func main, equals create user, test at example.com. If equals nil, var valor validation error. If errors as error and val error. fmt print, user input error. %s field, %s\n, valor message, valor field. Else, fmt print, unexpected error, %s\n error. This allows for much cleaner and more reliable error branching logic than checking error. Name cannot be empty. 4. Differentiate between recoverable and fatal errors. Not all errors are equal. Some errors, like a malformed request, are localized and can be handled without crashing the application. Others, like database connection loss in a critical system, might be truly fatal. Recoverable errors. Return an error value and let the calling function decide how to present it or retry. Fatal errors. If an error genuinely renders your application unable to function, consider log fatal, which prints a message and calls osexit, or panic. If it's a bug or unrecoverable startup issue that you know will crash the app eventually anyway. 5. Centralized logging and observability. While the if equals nil pattern forces local error handling, a complete strategy requires a robust logging system. Log context. When logging errors, ensure you capture sufficient context. Timestamps, source file line numbers, goes log package can do this, request IDs, user IDs, and any relevant application state. Structured logging. Use structured logging, e.g. JSON logs, with fields like severity, info, warning, error, fatal, error message, error type, stack trace, etc. This makes it easier for monitoring tools to parse and alert on errors. Trace IDs. In distributed systems, propagate a trace ID through your services so that all logs related to a single request can be correlated, making cross-service debugging much simpler. Metrics. Instrument your error handling to emit metrics, e.g., counters for specific error types, rates of errors. This allows dashboards and alerts to detect system health degradation. Import, log, us, func process request, error, simulate an error, return fmt error, storage access failed, %w, author permission, func main, equals process request, if equals nil, log print, level equals error msg equals / failed to process request / error message equals / %v / stack trace equals / %s / debug stack, example of logging detailed context. In a real app, you might also push this to a metric system. 6. Resource cleanup with defer. Go's defer statement is invaluable for ensuring resources are properly released, regardless of how the function exits, normal return, error return, or panic. Func process file, filename string error. F equals os open, filename. If equals nil, return fmt error, could not open file, %w Defer fclose. This ensures fclose is called when process file exits. Read from file, potential errors here. Data equals make byte 1024. Equals f, read data. If equals nil, return fmt error, could not read from file. %w return nil. This pattern greatly reduces the chance of resource leaks, e.g., open file handles, database connections, network sockets, and ensures that your application remains stable over time. 7. Avoid unnecessary error checks at call site when appropriate. While fundamental, the if equals nil pattern doesn't mean every single line needs an error check if the function's contract implies it can handle or recover from the suberror internally. Consider a write method on a custom type. Type mywriter struct. Output iowriter. Func mw mywriter, write message, msg string error. mw output write byte msg. If equals nil, here we decide to wrap and return, not handle locally. Return fmt error, failed to write message. %w return nil. In some caller. Func main, mw equals and mywriter output, ossd out. We expect write message to handle its internal details. We only check the error at this higher level. If mw write message, hello world \n, equals nil. Log fatelf, fatal error writing. %v, The point is not to ignore errors, but to place the if equals nil check at the appropriate logical boundary where meaning can be added or action can be taken. The write message function here encapsulates the IO-writer error, making the main function cleaner. Adopting a proactive mindset. Ultimately, robust error management in Go comes down to a proactive mindset. Instead of simply reacting to errors, you design your applications to anticipate them. By consistently applying error as value principles, using informative custom types, diligently wrapping errors, and integrating comprehensive logging, you build systems that are not only more resilient, but also significantly easier to debug and maintain when the inevitable, something went wrong, moment arrives. Such systems convert potential crises into mere diagnostic exercises, allowing your software to thrive in the face of imperfection. 8. Real-world scenarios and practical applications. Theory is one thing, but applying error handling principles effectively in real-world Go applications is where the rubber meets the road. This chapter will explore several common scenarios and demonstrate how to apply the idiomatic Go error handling patterns we've discussed, highlighting best practices and common pitfalls. Scenario 1. Handling external API calls. Interacting with external web services, REST APIs, gRPC, etc., is a staple of modern applications. These interactions are notoriously prone to errors. Network issues, API rate limits, invalid credentials, server-side errors 5xx, client-side errors 4xx, and data parsing failures. Problem: make an HTTP GET request to an external user API and parse the JSON response. Package main, import, encoding/JSON, FMT, IO, net/HTTP. User represents the structure of the data we expect from the API. Type user struct, ID string JSON, ID. Name string JSON, name. Email string JSON, email. Custom error for API-specific issues. Type API error struct. Status code int. Message string. Endpoint string. Error, the underlying network or parsing error. Func API error, string. Return FMT sprint. API call to %s failed with status %d. %s internal, %v. Endpoint, status code, message, error. Get user by ID fetches a user from a hypothetical external API. Func get user by ID, user ID string, user error. URL equals FMT sprint. https api.example.com/users/%s. User ID, hypothetical API URL. Resp equals HTTP get URL. If equals nil, network errors or client-side issues before even making the request. Return nil, and API error. Endpoint, URL, message, network or client error before request sent. Wrap the actual network error. Defer REST body close. If REST status code equals HTTP status OK, API returned a non-200 status code, e.g., 404, 500. Body bytes reader equals read all, REST body. If reader equals nil, return nil, and API error. Status code, RESP status code, endpoint URL, message FMT sprint. API returned status %d, but failed to read error body RESP status code. Reader. Return nil, and API error. Status code, RESP status code, endpoint URL, message string body bytes. Use the body as the error message. Body bytes, equals read all, RESP body. If equals nil, error reading the successful response body. Return nil, and API error. Status code, RESP status OK. Endpoint URL. Message, failed to read response body. Var user equals JSON and Marshall, body bytes, and user. If equals nil, JSON unmarshalling error. Return nil, and API error. Status code, HTTP status OK. Endpoint URL. Message, failed to parse API response. Wrap the JSON parsing error. Return and user, nil. Func main. Example usage. User get user by ID, non-existent d. Simulate a 404. If equals nil, fmt printf, error fetching user. %v \n, var API error. If errors is error and API error. fmt printf, API specific error details. Status equals %d, endpoint equals %s\n, API error status code, API error endpoint. If API error status code equals HTTP status not found. fmt println, user was not found. Please check the ID. In a real application, you'd log this error much more thoroughly. Else, fmt printf fetched user, %+v\n user. For a real test, you'd mock HTTP responses. Key takeaways: custom error types. API error centralizes all HTTP API specific error information, making it easy to inspect. Layered wrapping. Each layer network, HTTP status, body read, JSON unmarshal, wraps the original error, so the caller can distinguish the root cause using errors, is or errors as. Defer for cleanup. REST body close is deferred to ensure resource release. Examine status codes. Explicitly handle non-200 HTTP status codes as they usually indicate an error. Scenario 2. Database operations with specific error handling. Database interactions are a common source of application errors, from connection issues to unique constraint violations. Problem: insert a user into a database, handling unique constraint violations specifically. Package main, import, database SQL, errors, fmt, github.com/lib/pq. Example using PostgreSQL driver. Define a sentinel error for a unique constraint violation. Var duplicate user equals errors new, duplicate user entry. This would typically be in a data access layer repository. Func insert user, db SQLDB. Username, email string error. Query, insert into users. Username, email values $1, $2. Equals dbexec query, username, email. If equals nil, PostgreSQL example. Check for specific error codes for constraint violations. Actual error codes depend on the database and driver. For PostgreSQL, constraint violations are often 23505. var pg error interface code. String, using an interface to check for a code method. If errors as error, and pg error and an pg error.code equals 23505. Return or duplicate user. For other errors, wrap and return. Return fmt error. Failed to insert user %s. %w, username Return nil. Func main. Simulate DB connection, usually done once at app startup. DB, SQL open, Postgres. User equals PQ test DB name equals PQ test SSL mode equals disable. If equals nil, fmt printf, DB connect error. %v\n, Return. Defer DB close. Ensure DB connection is closed. Simulate first user insert, success. Equals insert user, DB, Alice at example.com. If equals nil, fmt printf, error inserting Alice. %v\n, Else, fmt println, Alice inserted successfully. Simulate second user insert, duplicate. Equals insert user, DB, Alice at example.com. If equals nil, if errors is error or duplicate user. fmt println, attempted to insert a duplicate user. Inform client and return 409 conflict. Else, fmt printf, unexpected error inserting second Alice, %v\n, Key takeaways, sentinel errors. Duplicate user acts as a clear, comparable indicator for a specific business logic error. Database-specific errors. Database drivers often expose their own error types or methods to inspect underlying error codes, like pgerror.code for PostgreSQL. Use errors, as or type assertions to access these. Layer abstraction. The insert user function encapsulates the database driver's specific error details, propagating a higher level, more abstract error, duplicate user, to its caller. Scenario 3. Contextual input validation. Input validation is fundamental. When validation fails, providing specific feedback to the user or calling system is crucial. Problem: validate user input for a registration form and report all validation failures. Package main. Import. Errors. FMT. Strings. Validation error represents a collection of validation issues. Type validation errors struct. Field string. Message string. Func v validation errors error string. var sb strings builder. sbWrite string. Validation failed \n. For e equals range v. sbWrite string fmt sprint. Field %s. %s \n. E field e message. Return sb string. User registration form represents incoming user data. Type user registration form struct. Username string. Email string. Password string. Validate performs validation on the form data. Func f user registration form validate error. var validation errors. If len f.username 3. Validation errors equals append. Validation errors struct field message string field. Username message must be at least 3 characters. If strings dot contains femail at. Validation errors equals append. Validation errors struct field message string field. Email message is not a valid email address. If len f password 8. Validation errors equals append. Validation errors struct field message string field. Password message must be at least 8 characters. If len validation errors 0. Return validation errors. Return the slice as an error. Return nil. Func main. Form equals user registration form. Username. Us. Email invalid email. Password short. Equals form validate. If equals nil. var valors validation errors. Use errors as to check if the error is our custom validation errors type. If errors as error and val errors. FMT println. User registration failed due to validation errors. For e equals range valors. FMT print %s. %s \n. E field e message. Else. FMT print unexpected error during validation. %v \n Else. FMT println form validated successfully. Key takeaways, aggregating errors. Validation errors allows collecting multiple validation failures into a single error object, which is then returned. The error method provides a formatted message for logging or display. Structured feedback. By defining the validation errors as a slice of message field pairs, the caller can iterate and present specific feedback for each invalid field. Errors, as for type inspection. Again, errors, as is used to determine if the returned error is specifically our custom aggregate validation error. Scenario 4. Retries with exponential backoff. For transient errors, e.g., network glitches, temporary service unavailability, retrying the operation can lead to success. Implementing a retry mechanism, often with exponential backoff, waiting longer between retries, is a common strategy. Problem: execute an operation that might temporarily fail, retrying a few times before giving up. Package main. Import. Errors. FMT. Log. Time. Transient represents an error that can be retried. var transient equals errors new, transient error, please retry. Some operation simulates an operation that might fail transiently. It succeeds after succeed after calls. var call count equals 0. Const succeed after equals 3. Func some operation, error. Call count ++. If call count less or equals succeed after. Log print some operation. Call %d failed, simulated transient error, call count. Return transient, return our sentinel transient error. Log print some operation, call %d succeeded, call count. Return nil. Func main. Const max retries equals 5. Const initial backoff equals 100 time dot millisecond. For I equals 0. I max retries, I++. Equals some operation. If equals nil. FMT println, operation succeeded. Return. If errors is error or transient. Backoff duration equals initial backoff time duration, 1i exponential backoff. Log print transient error at attempt %d. Retrying in %v. \n, I+1 backoff duration. Time sleep backoff duration. Else. For non-transient errors, don't retry. FMT print, operation failed with non-transient error. %v \n, Return. FMT print, Operation failed after %d retries, \n, max retries. Key takeaways, distinguishing errors for retry. Errors is error, transient, is crucial here to only retry for specific known transient errors. Other error types, e.g., not found, error permission denied, should not trigger a retry. Exponential backoff. The time duration, 1i formula calculates increasing wait times, preventing hammering the failing resource. Configurable parameters. Max retries and initial backoff should be configurable, e.g., via environment variables or a config file for real-world deployments. These scenarios illustrate how Go's error as value approach, combined with custom types, wrapping, and the errors is errors. As functions, provides a powerful and explicit framework for building reliable and resilient applications. By actively defining, propagating, and inspecting errors, developers can create software that not only functions correctly, but also behaves gracefully and informatively when faced with the inevitable complexities and failures of the real world. 9. Conclusion. Embracing Go's error philosophy. We have journeyed through the intricate landscape of error handling, starting from the foundational concept that errors are an inescapable part of software development. We explored the prevalent exception-based paradigms, understanding their strengths in separating concerns and propagating failures, but also acknowledging their complexities, potential for obscurity, and performance overhead. Then, we turned our full attention to Go, a language that consciously charting a different course, embracing the philosophy that errors are values. This core principle underpins everything we've discussed: explicit handling. The ubiquitous if equals nil pattern, once seemingly verbose, is now recognized as Go's insistence on explicit error checking. It forces developers to confront potential failures directly at the point of call, leading to a disciplined approach where errors are acknowledged and addressed, not merely caught as an afterthought. Simplicity of mechanism, depth of application. The error interface with its single error, string method is elegantly simple. Yet, upon this foundation, Go builds a powerful system through multiple return values, enabling functions to return both results and potential errors cleanly. Custom error types, allowing for rich, structured, and semantically meaningful error information. Error wrapping, %w, and inspection errors as, providing invaluable tools for preserving the chain of causation, enriching context, and allowing for programmatic introspection of error details at any level of the call stack. The special case of panic and recover. We clarified that panic is not Go's equivalent of exceptions for general error handling. It is reserved for truly unrecoverable conditions, programmer errors, or catastrophic states, or for acting as a safety net around Go routines in long-running services. Misusing panic undermines Go's clarity and predictability. Strategic error management. Beyond individual error checks, we looked at how to implement robust error management strategies. Never ignoring errors, enriching context, designing specific error types, differentiating error severities, centralizing logging for observability, and leveraging defer for resource cleanup. Real-world scenarios demonstrated the practical application of these strategies in common development challenges like API calls, database interactions, and input validation. The journey to idiomatic Go error handling. For developers coming from exception-heavy backgrounds, Go's error handling can initially feel like a step backward, demanding more explicit lines of code. However, as one spends more time in the Go ecosystem, a different perspective emerges. The verbosity transforms into clarity, and the explicit checks become empowering. This seemingly strict approach fosters a programming discipline that places resilience at the forefront. When you write Go code, you are constantly asking yourself, what can go wrong here? How should I react if it does? And what information do I need to pass up the chain for someone else to understand and potentially handle this? This constant consideration for failure scenarios builds more robust, predictable, and maintainable systems. Moreover, Go's error handling model aligns perfectly with its broader design principles of simplicity, transparency, and high performance. The absence of hidden control flow jumps, the minimal overhead of error returns, and the clear separation of normal and abnormal execution paths contribute to code that is easier to debug, reason about, and optimize. Beyond the book, continuing your learning. The principles and patterns outlined in this book provide a solid foundation. However, error handling, like all aspects of software development, benefits from continuous practice and exposure to diverse problem sets. Read Go source code. The best way to deepen your understanding of idiomatic Go is to read the standard library and popular open-source Go projects. Pay close attention to how errors are returned, wrapped, and handled. Experiment. Try creating your own custom error types, design complex error chains, and experiment with errorses and errors, as in your personal projects. Consider error policies. Think about how errors flow through your entire application. At what layer should errors be logged? At what layer should they be translated into user-friendly messages? And at what layer should they trigger alerts? This concept of error policies is crucial for larger systems. Engage with the community. The Go community is vibrant and helpful. Discuss error handling challenges, learn from others' experiences, and share your own insights. Final thoughts. The decision to treat errors as values is a hallmark of Go's design. It's a pragmatic choice that trades the perceived convenience of exceptions for the tangible benefits of explicitness, clarity, and control. By embracing this philosophy, by diligently if equals nilling, by wisely wrapping and unwrapping, and by reserving panic for its true purpose, you will not only write better Go programs, but also cultivate a deeper understanding of how to build reliable software that can gracefully navigate the uncertain seas of real-world operation. Errors are inevitable. How you handle them defines the quality and resilience of your software. In Go, you are given the tools to handle them with precision, transparency, and a profound respect for the undeniable truth. Errors, not exceptions, are just another value waiting to be understood.